Hello guys, welcome back to Maison African Motives. Still working on our Electrotechnics N4. That is in this platform. We shall be working on the capacitance. We shall just want to talk about the basics that we need to understand actually when we are dealing with capacitance in this case. So before we check this part that we have, we shall just have a basic introduction of this part that we are talking about as the capacitance. Remember, we talk of series circuits, parallel circuits in terms of resistance. We have the same condition when we are talking about capacitors. In this case, we can have capacitors that are connected in a series or capacitors that are being connected in parallel in this case, all right? So we've got capacitors in series in this case. What is going to be the condition whereby the capacitors are being connected in series? What is it that you are supposed to consider? Let us take note two capacitors in this case, or let us just say we've got three capacitors or whatever number of capacitors that you have. Remember, these lines are supposed to be of equal length, all right? So if these capacitors are connected to a voltage source, so let's say they are being connected to a voltage source in this case, which is our PD in this case, the voltage across. We've got the first capacitor, the second capacitor, and the third capacitor. So it means that in series, each capacitor is going to carry its own voltage drop. In this case, we shall have the voltage across this capacitor, the voltage across this capacitor, and also the voltage across capacitor 3 in this case. We are going to be talking of charge. A capacitor, it stores charge, whilst the resistor, we are talking about resisting current. So in terms of capacitors, we shall be talking of charge in this case, which is referred to as Q. That is the one that affects the capacitance of a capacitor. So in a series circuit, you are going to see that the charge is going to be the same throughout, just like current. Like I said, capacitors, they work with charge. You know that if you are dealing with current, current is the same. But here we are talking about charge in each. So the charge across, which is the total charge in this case, is equal because just like the same consideration of a series combination. So it's the same charge at capacitor 2, is the same charge at capacitor 3, depending with the number of capacitors that you are given, which is the same thing as the voltage. The total voltage is going to be the sum of V1 plus V2 plus V3. You combine the voltages together. But what's going to happen with the capacitance? Capacitors in series, they oppose what we understand about resistors. Take note, capacitors in series, they oppose to what we know about resistors, meaning to say, if capacitors are in series, they use what we know about resistors in parallel, the opposite now of resistors in parallel. So meaning to say, for the total capacitance, we are going to use 1 over CT is equal to 1 over C1 plus 1 over C2 plus 1 over C3 and so on, just like resistors in parallel is the opposite. But remember also, we've got a special case when we are given two resistors in parallel, we use product over sum. It is the same condition when you are given two capacitors in this case. So given two capacitors, we can apply the product over sum. When given two capacitors, the total capacitance can be from the product over sum. That's C1 times C2 over the sum of C1 and C2. We are going to apply the product of the capacitors over the sum. So the charge here is measured in coulombs. So this one is measured in coulombs in this case, which is used the letter C. The voltage is measured in volts. Our capacitance is measured in farads in this case. So the unit farad is the unit for what? Is the unit for capacitance, which is the farad in this case. The unit farad is simply the unit for measuring the capacitance. All right, so this is what you need to understand if you are dealing with the capacitors that are in a series connection. In place of current, we use charge, just like charge. But the total capacitance, we use what we know about resistors in parallel. That concept of resistors in parallel, that is the one that you apply, which is the opposite now if these capacitors now are in parallel. So we can have these capacitors in parallel. So that is the whole idea, that you just need to know the basics. So if we are given capacitors in parallel, let's say we've got 3 capacitors, just like the previous case that we had. We also have the third capacitor here. All right, so connected to a voltage source. So this time we've got a voltage source here connected together. All right, so let us say these are the capacitors that we have in this case, C1, C2, C3, connected to a voltage source. So let's say I've got C1, C2, and C3. All right, and we have our voltage source in this case. Remember, I said in capacitors, we talk of the charge instead of the current. Yes, the voltage here is going to be the same. We're talking about a parallel combination whereby the voltage is the same throughout. So the voltage here across C3 is the same as the voltage across C2, is the same as the voltage across C1 in a parallel combination. So V is the same as V1, is same as V2, is the same as V3. But let us take note, if we are talking about, let's say, current, from our understanding of our resistors, we know that current branches in each and every branch. So it is the same condition as what we are going to have in this case as in terms of charge. There is going to be the charge across C1, the charge across this, the charge across this. So, and we've got the total charge of the circuit. So the total charge this time is going to be the sum we are going to add. That is going to be Q1 in this case. So we are going to have Q1, which is the charge 1, plus the charge 2, plus the charge 3 over the given circuit, just like current. Just like current, as we are working with the charge. What is this charge that we are talking about? That we are simply saying charge is simply the product of capacitance to the voltage. The product of capacitance to the voltage, that is the charge. So meaning to say, if we are to use this, we are simply saying Q1, in this case, the charge at this point here is going to be voltage times capacitance times voltage, or voltage times capacitance. So it's going to be C1 times V1, whereby we said V1 is equal to the total voltage. So it's going to be C1 times V, which is V1, the one that we have as our supply voltage. The same thing that is going to happen to charge 2 is going to be the capacitance there times the voltage that is for the parallel combination. The voltage is the same. The same with the Q3. So it's the same thing even here. If we multiply the capacitance and the voltage, you obtain Q1, Q2, Q3. So that's the product that you're going to have. All right, I'm worried about the capacitance here. What's going to happen with the capacitance in a parallel combination? Like I said, capacitors, they oppose resistors. So the total capacitance is going to be the sum we consider as resistors in series. We are in parallel. So it's the opposite we consider as resistors in series. We are going to add C1 plus C2 plus C3. So these are the most important conditions that you're supposed to note about the charge, the voltage, the capacitance. Oh, we shall have another class actually with more questions to consider. But for this one, I just want us to consider this part here. The first part we're given to define the term farad. So as we can see from our combination, this is just the unit of measurement of what? The unit of measurement of capacitance. So we can name it as 1 farad. In this case, 1 farad is the capacitance. All right, 1 farad is the capacitance which will, all right, is the capacitance which will accumulate. All right, this is the capacitance that will accumulate that will accumulate a change of 1 coulomb in this case, which is the charge of 1 coulomb, which is our charge in this case, all right, when connected across a voltage, all right, across a voltage of 1 volt in this case, across a voltage of 1 volt. So you can simply define in this way, but this is simply the unit of measurement of capacitance, all right? So that is how we can play around with this information. All right, so let us check question. The second part, we are given 2 capacitors connected in series. Remember what we said about a series combination? That is the condition of resistors in parallel. So we've got 2 capacitors in this case that are connected in series. After this, we are given that to we got respective readings. So we have given the readings of the capacitors, in this case of the voltages across the capacitors. So definitely they are going to be connected to a DC supply, in this case like this. Then we have got the voltages across the first capacitor, the second capacitor, 18 volts and 6 volts. So here there's a voltage of 18 volts, and here there's a voltage of 6 volts. These are the voltages across. That is, we are talking about V1 and we are talking about V2. All right, according to this. Then if the total charge equals to, remember I said the total charge is like current, the current flowing. That is how you take the charge. It's just like current. All right, so given the total charge is equals to 1,800 microcoulombs in this case, microcoulombs, determine the following: the total capacitance. All right, how are we going to determine the total capacitance from this information? All right, from the part that we talked about, we said if we are given in this case the total voltage, because we know that Q can be taken from the capacitance times the voltage in this case. So if we are talking about the total charge, it must be total capacitance, it must be total voltage. So the question needs us to calculate the total capacitance, meaning to say we can play around this formula to say the total capacitance is going to be the total charge over the total voltage. But asking ourselves now, we can see that we have the total charge, yes, but we do not have the total voltage. Where are we going to obtain the voltage from? Remember what I said, in series, the voltages, you add them. In parallel, the voltage is the same. So meaning to say we can calculate the total voltage from these 2 voltages that we are given. We've got the voltage across the first capacitor and the second capacitor. So that means V1 plus V2 in this case is supposed to give us the total voltage. So that means our total voltage is going to be 18 plus 6, which is going to give us 24 volts in this case. So having the total voltage of the second, we can calculate the total capacitance because we have the total charge already here. We have got our total charge. So that means the total capacitance was going to be the total charge. That's 1,800 times 10 to the exponent of -6. Remember, micro, that's times 10 to the exponent of -6 over the voltage, total voltage of 24 volts. Remember, our capacitance is measured in farads in this case, all right? So it is best for us to have our answer in microfarads, and already this 10 to the exponent of -6 here means micro. So instead of us using this on our calculation, we can simply divide these two. We can simply divide these 2 on your calculator so that you already remain with a micro there on your answer. So if you divide 1,800 to 24, you are going to obtain 75 in this case, already having times 10 to the exponent of -6, which represents a micro. So that means that is going to be our capacitance, 75 microfarad. We have the total capacitance of the circuit from the voltage. Then after that, the question needs us to calculate now the value of each capacitor. Each capacitor that we are given, what is going to be the value of each capacitor in this case? All right, taking charge, because we said charge represents the same way as current. So in a series, we are going to see that the charge there is the same, because that is what we know about the current. So meaning to say here, we are going to experience the same charge, which is our total charge in this case. And we have the voltages across each. So we can use the same formula to find the value of the capacitors. Remember, we said in this case, charge is capacitance times voltage. Now we need to calculate the capacitance of each part. So meaning to say, we are going to obtain something like this. Across C1 in this case, our capacitance is charge over voltage. So we are supposed to have capacitance as a charge over the voltage. So if we are talking about C1, this is supposed to be V1. This is supposed to be Q1, but in this case, we are saying Qt is equal to Q1 is equal to Q2. We are talking about in a series, charge is the same. So we are simply going to find this direct. That is the charge of 1,800 times 10 to the exponent of -6, which is micro, divided to the voltage across capacitor 1, which is 18. So like I said, our capacitance is measured in farads, and mostly we can use our units as microfarad. So this 10 to the exponent of -6 already represents a micro. So just divide these two numbers here. You are going to obtain 100. So this is going to be 100. The 10 to the exponent of -6 represents a micro. So that is 100 microfarad. That is the capacitance that we are going to have at what? At this value that we have. But remember, we also talked of product over sum. We are going to prove that later on. All right. So let's see this one. Meaning to say, for us to calculate the one across C2, C2 is going to be the charge again over the voltage, but voltage across C2. So that means the charge is the same. The charge here is the same. So we're going to use 1,800 times 10 to the exponent of -6 over V2, the voltage across the capacitor, which is 6. So that was going to give us C2 already. 10 to the exponent of -6, divide these two so that your answer is going to be in microfarad. So this is going to give us 300, our answer in microfarad in this case. So if we are to check this part, remember these two, they are in series, and we said capacitors in series, they relate as capacitors in parallel. So it must be of proof that these two combined together should give us the total value that we are given. Remember, if they use the same concept as resistors in parallel, meaning to say CT can be from product over sum, we can use the product over sum. Since we are given two capacitors, yes, we're supposed to use 1 over CT is equal to 1 over C1 plus 1 over C2, which is fine. But we can just use product over sum because we are dealing with the two capacitors in this case. So meaning to say we can prove this 100 multiplied to 300 in this case over the sum of C1 and C2, which is 100 plus 300 in this case. So let us see what we are going to obtain from our CT already. These values, they are in micro. So meaning to say our answer is going to be in micro. So let us check on our calculator here. That is going to be 100 times 300 in this case. All right, 100 times 300 over the sum 100 plus 300 in this case. This is going to give us a 75. So we are obtaining 75, just like the same answer that we had for the total capacitance. So this can be just a proof that you are having to check if your values, the ones that you calculated as capacity, as the value of the capacitor 1 and the value of the capacitor 2 are actually corresponding to the total capacitance, because you calculated that total capacitance before. So meaning to say you can use that as a proof to check if they do correspond to the value that you expect to get. So that's the typical questions that you might be given. So like I said, we shall have more questions checking on the parallel combination and some other typical questions that they might ask. But for our introduction part, these are the formulas that we need to understand and apply them for a series and the one that we listed for a parallel. So we can play around those formulas and try to attempt questions so that when we come back again with another class, you'll be having an understanding of what you're talking about. So use the formulas, try to answer question papers with those formulas. You'll see that you can attempt any question that you be given on capacitors. That is the idea there.